Okay.
Mhm. And you see the main presentation, not the presenter's slides, right?
Yes, I see a full screen
Okay.
as it should come across. Yeah.
Okay, perfect. Thank you.
Okay, so it is 11:30. Welcome back, everybody. Now we have our invited talk, and we are very grateful to have the chance to present or to host a presentation from Sonova. Sonova is one of the world's largest hearing device manufacturers. That includes hearing aids, cochlear implants, and hearing assistive systems. Um, so they are confronted every day with how do you get these wonderful systems out there into the real world and used and usable by the people who need them. So I'm sure we're in for a very interesting presentation, which will be presented by Stefan Raufer, who is a senior research engineer at Sonova and has been deeply involved in the development of their newly or relatively newly launched hearing aid system, which includes DNN-based denoising, and Peter Derlet, who is the Senior Director of Hearing Performance in Sonova. So Stefan will be presenting the talk, but Peter is also here in the background, and both of them will be available for questions and answers afterwards. So without further ado, I think I'll hand over to Stefan to give the talk.
Great. Thank you, Graham, for the introduction and for inviting us to share some of our newest innovations. Thanks also to the students and contributors for giving their talks. It's tremendous to see your interest in the technology, and that's also very inspiring to me. We're all here, we are working on the same problem, and that is to solve the speech understanding in noise problems for hearing impaired people. So before we throw a technology at this, I want us to understand the auditory system a little better. Here on the right side, we have a graph that shows the dynamic range on the y-axis and the frequency range on the x-axis of a healthy human ear. The ear has a tremendous dynamic range of 120 dB, which in a linear ratio comes out as a 1 to a million, or a power ratio of 1 to the 10 to the power of 12, 1 to a trillion. We can distinguish levels of 1 dB, and the loudness is somewhat related to the level, but twice the level does not correspond to twice as loud. Twice as loud is about increase in 10 dB. The frequency range of a healthy human ear covers 20 hertz to 20 kilohertz, and we can distinguish about a change in 1% of the frequency, which if you take the A4 on a piano as an example, we could distinguish 10 semitones, a tenth of a semitone for that key. This is the so-called speech banana that we use in audiology, and the speech banana covers the levels and the frequencies where the speech sounds, the vowels and consonants are located. We have a look at the anatomy of the ear, starting from the pinna, the outer ear, the ear canal, the middle ear, and the cochlea. Then damages to the ear can arise really at every stage of the auditory pathway. So damages to the outer ear and the middle ear are of mechanical origin and can be either fixed mechanically, or in this case, amplification is also sufficient. If the damages happens in the cochlea or beyond, then amplification is not sufficient to fix the problem. But in current days, we need hearing aids or cochlear implants to rehabilitate that damage. And here's a picture, electron microscope picture of the inner ear showing a row of healthy inner hair cells and 3 rows of healthy outer hair cells. But if these cells get damaged, I'll show a photo in the in this graph where the outer hair cells are damaged. Then we are faced with 3 problems. First of all, the loss of inner hair cells increases the hearing threshold, and the damage or the loss of outer hair cells reduces the dynamic range, and it reduces the frequency selectivity. So a simple amplification is not sufficient to fix the hearing problem. Then we are pretty much focused on the periphery so far, but of course, in each stage of the auditory pathway, from the cochlea to the brainstem, the midbrain, and the cortex, hearing loss leads to structural and functional changes. The consequences of unaddressed hearing loss is that we have reduced speech understanding, especially in noise. For the same speech understanding, hearing impaired ear requires a much better signal to noise ratio. And hearing loss also impacts cognition. Uh, Back to this graph, if we would plot a normal hearing threshold in this graph in like an audiogram style, then hearing loss comes in different degrees, from a mild hearing loss to a moderate to a severe and a profound hearing loss. The audiogram really only shows the audibility loss. It is the most used test that tries to objectify the hearing, but it's really only capturing the hearing status at threshold and does not capture perceptual consequences of hearing that go beyond just the hearing threshold. And from those degrees of hearing loss, you might also think that one type of denoising solution is not sufficient for every type of hearing loss. And if we have the goal of doing individualized and personalized medicine, then surely one fits for all is not sufficient. Before we speak about our latest innovation, I wanted to review some innovations in the hearing industry over the past 40 or 60 years or so. So hearing aids were really always at the tip of innovation. When transistors were invented in the 1940s, only a few years later, hearing aid manufacturer picked up that technology and put transistors into pocket-worn devices. When integrated circuits, ICs, were invented in the late 1950s, and only a few years later, this new technology was used and put into hearing aids, into a wearable solution. The first behind the ear hearing aid that could be worn on the ear was launched by Phonak in 1960. And since the early 2000s, hearing aids are fully digital. And now we have a hearing aid on the market with an AI chip. So I said in the beginning that for the same speech understanding, a much better signal to noise ratio is needed for people with hearing loss. And so far in the last 40 years, this problem of improving the signal to noise ratio has been addressed by directional microphones, by beamforming. Up until the 80s, a hearing aid would only have one single microphone, which later changed to include 2 microphones. And with these 2 microphones, a directivity pattern could be generated so that sounds from the back are attenuated. And as such, if you have a target source in the frontal plane, the signal to noise ratio would increase. In those early days, the fixed directional microphone was fixed on the hearing aid and could not be changed. Only in the 1990s, there was a remote control where you could change that configuration from a single microphone omnidirectional to a two microphone static directional setting. But the performance of using the directivity of two microphones plateaued. We can achieve about a 3 dB increase to the front, but not much more. In the 2010s, a technology using the two microphones on each sides and connecting them through a binaural link was launched on the market. And Phonak uses the feature name Stereo Zoom for it. It's a binaural beamformer. And with this technology, another 3 dB could be achieved in terms of SNR improvement to the front direction. But what comes next? We don't want to add 8 microphones or another pair of hearing aids on the ears. And we believe that the future lies in a combination of DNN-based denoising with directional microphones. If we look back 1 year in time, last year, then a group of hearing scientists from the Chinese Academy of Sciences and Brian Moore from the Cambridge Hearing Group published a paper that outlines the challenges of DNN-based speech enhancement methods for the use of hearing aids. And the first was the computational complexity. If you compare it to a hearing aid processing unit at that time last year, then we would need about 50 times more computation and about 10 times more memory to deploy a useful speech enhancement DNN on the hearing aid. The second was the delay. Current digital hearing aids run at about a 6 or 7 millisecond delay, and introducing another delay from a DNN speech enhancement system would double that delay, which would deteriorate the sound quality and maybe even the acceptance of the users. And there would be a lot of effort needed to develop such a thing. And the real life applications, like the latency, the open coupling, because most of the hearing aids that are sold are worn with an open or somewhat open vented coupling. So you don't get the benefit of the speech enhancement algorithm to the ear at low frequencies, but only at frequencies above about the kilohertz or 700-800 hertz. And how would that work? Would that benefit in that frequency range be enough? And then earlier this year in August, we launched a new hearing aid, the Phonak Audio Infinio Sphere, that has a co-processing unit, a dedicated DNN chip with an MPU architecture that has about 50 times more processing power and runs a deep neural network with 4.5 million parameters. It is implemented in the hearing aid in a way that it has to work with the rest of the hearing aid, right? So we still have the beamforming in the hearing aid. We still have features like feedback cancellation, wind noise cancellation that are done in a traditional way. We have conventional noise reduction algorithms still running, and we have the whole gain model in the hearing aid. And the DNN is implemented in the hearing aid in a way that it comes after the beamforming, but before the gain model. And we we only turn it on situationally. So the speech enhancement DNN is not running 24/7, but only in the most challenging environments at about 70 dB background noise level and above. So this DNN denoising unit lives in the architecture of a hearing aid. It increases the delay, it increases the power consumption, and we have a separate chip. It gets situationally activated. What we hope to get in return of it is the improved speech understanding for hearing impaired people in challenging environments. Next, I would like to talk about our three-pillar approach to developing the denoising DNN. It's not just about the denoising DNN, it's also about developing a chip that can host this DNN. And we developed also a training metric, audio quality estimator to train the DNN. To speak on the DNN architecture, here we see a picture of the macro architecture. It's a UNet structure. It's a encoder-decoder model. The encoder part is a convolutional network that transforms the SDFT into an abstract representation. We have an RNN, a recurrent neural model, that captures the temporal aspects of speech, and the decoder, which transforms the abstract representation back to a complex ratio mask. And this unit structure also has skip connections that supports the learning process. The final network is found in an evolutionary search where the number of layers in each block, the type of layer, the kernel size, the number of filters for each layer, the dilation rate, and the number and the location of the skip connections is determined. And if you're interested about the details on this architecture, you can read it up in one of our papers that came out last year in scientific reports. There are also other architectures nowadays that are worked on. Back then, when we started the development, this unit structure was pretty much a state of the art and was a good network architecture to solve the problem at hand. So the next pillar, the development of the chip. Here we see a plot of the computational power as a function of power consumption. Both of these axes are log scaled, and a few examples of where data centers or mobile phones or low power technologies lie here. We have three requirements. Basically, the first of all, we can choose. It's the hardware efficiency. The second is the power limit of on a hearing aid. We can't really spare more than 1 to 10 milliwatts to run such a DNN. Otherwise, the battery would run out of power by the end of the day. And the third is the demand for a useful denoising DNN. So this is the area, the computational power and the power consumption, where the network has to lie in order to run on a hearing aid. And as an example, this blue dot is a network that was used by us in a clinical study about 4 or 5 years ago, where the DNN denoising technology was used in a clinical study to see whether we can improve the Oldenburger Satz test SRTs. Right next to it, this was a similar study a few years later where we used a similar model, an improved model, but we ran it on a mobile phone, on an iPhone 5 or 6 or 7, I believe. And to close this gap, there was another couple of years development needed to get the performance power consumption ratio down. And the third pillar in bringing this new innovation to the market was to train a DNN, to have a DNN training metric, where we have audio snippets rated by human raters for 3 dimensions: noise reduction, sound quality, and the overall quality. And from these, we built an audio quality estimated DNN. I will spend more time, quite some time in the next slides on this Q-metrics model. And so to summarize our approach, we not only built a DNN architecture, a denoising DNN, but we also developed a training metric, and we co-developed the chip at the same time to bring this denoising DNN onto the market and have a successful launch with that. On the next slides, I would like to spend some time on how we developed the Q-metrics model. We saw 3 presentations today about activities going on in developing and improving denoising DNNs. From our view, as important is to have a good metric that can be used during the training process. We saw in these presentations, oftentimes the Husby model was used. This is an alternative approach to use a DNN-based metric during the training process. And again, if you're interested in reading up on the details, we have a paper published on that in PLOS ONE. You're welcome to read the paper as well. The Q-metrics model is a non-intrusive model for audio quality rating. It is broadly generalizing and has a high quality of prediction. We use it for closed loop optimization of denoising and speech enhancement DNNs, and for example, to find the best architecture and parameterization of various speech enhancement algorithms. One motivation to develop this was to replace the very expensive and time-consuming subjective listening experiments. I will go through the 4 stages of creating the Q-metrics model. The first is data generation, the second human ratings, the DNN training of this training metric, and the ensemble selection. So for the data generation process, we had about 15,000 noisy audio files created in various ways. They were pre-processed with a number of speech enhancement DNNs, but also classical speech enhancer algorithms. After they were processed, we had a data set containing about 35,000 samples. We had those 35,000 samples rated on Amazon mTurk. We screened about 1,000 people, and in the end used about 340 people that had a reliable setup and were reliable voters where we collected the data. We collected about 900,000 ratings over a time period of 7 weeks. Each sample was rated 9 times by the raters in the 3 categories: overall, noise, and sound quality. Then about a year later, we collected another 100,000 ratings for a validation test set. And at the time when this Q-metric was developed, we had more than 20 times more unique noisy speech samples than the next largest data set possible. Then we trained 20 candidate DNNs for the Q-metric, and 5 of these 20 trained networks were selected to form the final ensemble. These were 2 types of DNNs. We trained 9 convolutional neural networks with a ResNet architecture that takes SDFT features as input. And we had 11 simple dense networks with WAV2VEC feature encoders that uses the raw waveform as input. All of these networks were given, the architecture was identical except for the random seed to initialize the weights. And last but not least, the ensemble selection. 5 out of these 20 trained DNNs were used to form the ensemble. These consisted of 3 SDFT inputs and 2 using the WAV2VEC inputs. We chose the ensemble with the best combined performance. You see that the correlation up here with the ratings, overall noise and sound quality for this ensemble. Using more or including more networks increases the performance only ever so slightly, about 2%, but the prediction error goes down by almost 10%. So that's why including more DNNs, combining more DNNs into the ensemble was useful to reduce the prediction error. Lastly, the performance evaluation. To evaluate our Q-metrics DNN, we used 3 external data sets, the WAM-WOX Easy, WAM-WOX Hard, and Valentini. These test sets are processed with 5 different publicly available speech enhancement algorithms. So these is not our DNN denoising algorithm, but independent algorithms. And we compared our Q-metric to other metrics. This was 2 DNN-based non-intrusive metrics, one from Microsoft and one from Technical University of Berlin, and then 3 classic intrusive metrics, the eSTOI, CSII, and yeah, I'll save you this mouthful, or save myself this mouthful. These are the results. We can quickly walk through them. On the y-axis, we have the 3 data sets, WAM-WOX Easy, WAM-WOX Hard, and the Valentini, processed with these, or unprocessed and processed with these 5 algorithms, each of the test set. And we have the metrics on the x-axis. And you'll see that the Q-metrics overall has a better correlation to the subjective ratings over the reference non-intrusive metrics. The intrusive metrics perform similarly good, but our non-intrusive metric is more accurate than the existing intrusive and the existing non-intrusive metrics. And this model generalizes very well. And again, to highlight the largest difference to the other DNN-based metrics is that we have a much larger number of human ratings and a wider range of sound types that are trained. You can access this tool online, also using this link, metric@audatic.ai. And for sound demos of the denoising DNN, you will find those as well on the same website. So now I praised our metric, but it's surely not the last metric that will be developed. There's many ways of how our metric and our metrics can be improved. Most metrics are based on monofiles still today. There's no good metric for predicting, for example, the binaural quality, room characteristics, or spatial characteristics to evaluate even binaural denoising DNNs. And there's no good metric for predicting source locations. Also, most models are trained with ratings from normal hearing people, and the metrics could be improved by collecting more data from people with hearing loss also. Because that's difficult, one can also think of doing this model driven and simulate ratings of hearing impaired people. So this is an advertisement also that your future work in developing denoising DNNs should also or can also have an eye on improving and developing training metrics. In the second half of the talk, I would like to speak, or the last third of the talk, the next couple of slides, I'd like to speak about the clinical study results. That's very important for a medical device manufacturer that bringing a product on market, having simulations done based on model predictions and ratings from normal hearing listeners is not enough. We have to show the performance of the medical product that it's actually helping people with hearing loss. Otherwise, we would not, we would not be allowed to launch such a feature even. So we started the presentation with this slide and ask, can speech intelligibility be improved with technology, and can DNNs prove speech intelligibility? And the answer is yes. We conducted a clinical study with 27 experienced hearing aid users that had a moderate to moderately severe bilateral hearing loss using custom earpieces. And we measured the speech intelligibility and listening effort in a setup like this. There was noise coming from 5 different directions, and target speech also presented from these speakers. As far as improvements in speech intelligibility, with this DNN-based denoising, the marketing name is Spheric Speech Clarity. An average performance increase of 13% was achieved. This is from the feature turned off to this feature turned on. So you might say that 13% is not a lot, but the study design of this study was that we turned off and we turned on the feature. So there's no other changes in beamforming or aided versus unaided in here, but this 13% improvement in speech understanding comes only from the DNN feature. Compared to hearing aids of other two premium hearing aid manufacturers, the hearing aid with the DNN-based denoising system has a two times more likelihood to give the correct response compared to the competitor one. And it was this guy, I believe. And 3 times more likely to give a correct response compared to another comparator. Listening effort is another clinical outcome measure that is used to show the performance of a hearing aid. And the goal of this listening effort study is, or the outcome is to basically you have the ratings of how effortful it is on a scale from 1 to 13, no effort at all, to very effortful. And you measure the signal to noise ratio at which you get these ratings. And with the DNN denoising feature on, the SNR at the, the equivalent rating could be about 3 dB worse. So instead of, let's start with the very little effort, an SNR of 0, with the DNN denoising in the signal chain, the input SNR could be at -3, and the perceived listening effort was the same as when the feature was turned off. So to summarize this clinical study, we demonstrated a clinical benefit of the new DNN-based denoising technology. As a hearing aid manufacturer, we have to use clinical claims if we want to market the performance. We showed that the DNN-based denoising can improve speech intelligibility and listening efforts. And now these are two worlds colliding, and all of us are in the middle of it. There are these requirements from the FDA in the US, the MDR, and other institutions around the world. And there's AI engineers who develop the technology. Clinical studies are not practical in the training process at all. They are not even practical in evaluating DNN denoising during the development phase, but the clinical study comes at the very end of the development chain. And so here, again, this is to show the motivation to develop and use sophisticated evaluation metrics, computational metrics, before we go into clinical studies. Then I wanted to use this slide to reflect self-critically about what is currently used in marketing material of our competitors, but also by ourselves to show the performance of an algorithms. And many times we use the SNR improvement as that measure. But at the SNR improvement, so in this graph, the SNR improvement is shown for a static noise source and for a more realistic noise from the RT database. And what I wanted to show is that we can choose the test material wisely, and you can achieve the performance that you want to achieve, right? By just showcasing one example where it works really well. And this example for a conventional noise canceling single channel Wiener filter could be a static noise. With those, you can achieve an SNR improvement of 10 dB. And a DNN-based denoising system that was trained on years of audio data might not actually perform better in this static noise scene. As opposed to when we go to a realistic environment. And again, this is the reason why I chose this is also to demonstrate that maybe the DNN-based system is better in dealing with real-world environments, and a traditional noise canceling system is not working as well. But what I want to say is that looking into the future, we need to build more trust in using statistical metrics, not just choose one speech and noise scene where we show that it works well, but use more statistical metrics where we use a lot of scenes and can evaluate the performance in a much wider range of SNRs, background scenes, speech material. But building this trust internally, so inside the R&D departments, but also in the marketing departments and with our consumers and clients, it takes time. And as an example, in most of the presentations this morning, the Husby model was used as a evaluation metric. This metric was developed 10 years ago. So even at the level of the university, it takes 10 years for a new metric to latch on. And uh, here again, currently the evaluation metrics are lacking the technology. And in order to show the benefit of new technology, new evaluation metrics are needed. But these new evaluation metrics need time to sink in, and it needs time to build trust for these new metrics. Last but not least, I have 2 or 3 more slides to talk a little bit about the constraints of wearables and hearing aids. We in the beginning of the presentation, we talked about the low power constraints, the latency constraints, and that oftentimes hearing aids have an open acoustic coupling. And in the next slide, I would like to talk about the importance of those. So why is occlusion important? If we fit a hearing aid with an open dome with a very low acoustic mass, then we have a better wearing comfort. The sounds around us sound more natural, and also the perception of our own voice is more natural. There's no occlusion effect. So using an open fit has many advantages. Using an occluded fit also has many advantages. The sound cleaning features work better. We can achieve better intelligibility with beamforming and noise canceling. We have much better streaming quality if you connect the hearing aids to your phone. And we have a lower risk of feedback because the acoustic path is occluded, which means we can provide more gain to counter the hearing loss. And it's really a trade-off of those more natural, more comfortable open wearing versus the occluded. But in reality, most of the hearing aids are fitted more on the open side. What we do in our product is that because noise canceling is less effective in an open coupling, we increase the strength of the DNN denoising. We are more aggressive. And we can do that because there's more direct sound coming from the environment, and this direct sound also helps at masking some of the artifacts that the DNN is introducing. This next slide is to speak about a latency and the COM filter that we get by introducing a delayed sound path. So the sound at the eardrum is the sum of the direct sound from the environment plus the processed sound from the hearing aid. And that comes with the delay of 6 milliseconds. With the DNN chip active in the phonak devices, it's about 15 milliseconds. And that's a problem because if the gain of the hearing aid is about the same as that of the environment, which is the case in louder environments, then we get this COM filter, which sounds very unnatural, and people are disturbed by it, by the sound of their own voice and also by the sound, by the environmental noise. If we apply more gain, then the problem becomes less prominent, but choosing how much gain we apply is also something that we can't choose. It depends on the level of the environment and it depends on the type of hearing loss. So getting this delay down is important. And what we found is that as long as we keep the latency, the end-to-end latency below about 15 milliseconds, then that will be accepted by our users. And the next slide will show that. Here, the sound quality of the own voice is plotted as a function of the latency, and you see that it takes really a deep dive once we go above 25 milliseconds. This is also the case for the investigator's voice. This is for normal hearing. This is for a mild to moderate hearing loss. They are very similarly susceptible to that latency. What's interesting is that people with a severe hearing loss, they seem to be less susceptible for this. So here we identify a possible solution that for people with a severe hearing loss, or even for people with a cochlear implant where the direct sound doesn't matter as much and they rely on the amplified sound, that we can afford DNNs potentially with end-to-end latency that is larger than the 15 milliseconds. And that brings me to my last slide, and we will still have some time for questions afterwards to the conclusions. The DNN denoising has advantages over classical noise cancel. It actually improves speech understanding. It generalizes and is robust for complex scenes. I highlighted the co-development of the denoising DNN, the training metric that is used for the training and architectural search for the denoising DNN, and the chip design. We spoke about that each hearing loss is unique. Hearing loss affects not only the threshold, but also the dynamic range and the frequency selectivity. And for personalized medicine, we need in the future also personalized denoising DNNs and possibly even metrics. For a hearing aid manufacturer, it's important to consider the constraints of wearables, which is the power consumption, the latency, and the occlusion or the acoustic coupling. Yep. Denoising metrics and denoising DNNs, we're only at the beginning of that now. And in the future, we hope that the field, including yourself, will be able to improve and come up with new designs that improves the denoising DNNs and the metrics. And with that, I thank you for your attention. And we are open for any questions.
Stefan, thank you very much indeed for that fascinating presentation, which included a very nice tutorial on the ins and outs of how you have to design things for actual practical hearing aids, which is one of the areas which is probably less familiar for most of the listeners today. So that was really nice, and